Hey guys! All right, today we're going to talk about rotational kinetic energy. Okay, so what I've got here is a little bootleg ramp set up from one of our tables. And we've got about a 5-degree incline along this ramp, and we're going to send some objects down there to see what happens, all right? So the two objects we'll be sending down are a can of soup or a can of beans, and this one is full, so it acts kind of like a full solid cylinder. And then I got another can of coconut milk, but I've hollowed this one out, so it's basically a hoop or a hollow cylinder. All right, so these two objects, if we drop them in the air, right, they should accelerate at a known rate, at about 9.81 meters per second squared, give or take air resistance, right? And we know that if we put them each at a specific height, they're going to have some potential energy, mgh, and once they get down to the bottom right before they hit the ground, they'll have some kinetic energy, 1/2 mvf squared, right? 1/2 times their mass times their final velocity squared. And since they start with something that is proportional to their mass and end with a kinetic energy that's proportional to their mass, then the height they start at will be proportional to their final velocity. And given, again, they have the same acceleration, we would end up with the exact same amount of speed right before they hit the ground, even though they're two separate different objects, right? So let's see how this happens when we send them down a ramp. Because the difference here, right, is that we have two different objects, again, different shapes. This one's a solid cylinder, this one's a hollow cylinder, right? And we send them down the ramp. If we put them at this same height right here, they should have the same gravitational potential energy relative to their mass. And down at the bottom, they should end up with the same final velocity because, again, their kinetic energy is relative to their mass. So, if we take and we let them go, we find that our solid cylinder ends up with a greater final velocity because it has a greater acceleration, right? Now again, what we should be thinking is when we think about the energetics here, right? They start off with proportional to their mass, the same amount of potential energy proportional to their mass, but they end up with a different amount of kinetic energy proportional to their mass. So where is that difference going? That's what we're going to talk about in today's lesson. So we've already seen that two balls, one that's hollow, one that's solid, will roll down a ramp at different rates. And now we've seen the same thing with our soup cans, right? That if we take a soup can that's hollow and a soup can that's solid, they'll roll down the ramp at different rates. However, again, proportional to their mass, their gravitational potential energy at the top of the ramp should end up unlocking an equivalently proportional to their mass amount of kinetic energy at the bottom of the ramp, giving them the same final velocity once they reach the bottom of the ramp. However, that's not what happens. So where is that potential energy going that should be converted into kinetic energy for both of them, but ends up being converted differently into different amounts of kinetic energy between the two different shapes? And obviously, as you think about that, you're probably already considering that most of the stuff we've talked about so far in this class has been related to translational motion. And now that we're starting to think about rotational motion, there is going to be some amount of energy that's involved in rotational motion. And so, depending on how quickly those soup cans or those balls start to spin, they're going to have different amounts of rotational energy. And let's explore what that means. So let's first think about work in rotational motion. And again, we're going to return to some pictures that we thought about at the beginning of a rotational motion, Unit 5. We've got our spinning disc over here, and it is spinning in a counterclockwise direction. And the amount of distance that's covered as we go through some amount of motion, it can either be described by our rotation angle or our angular displacement or our arc length, right? So that distance we go along the arc of the circle. And so if we derive a formula for work in rotational motion, we can start off with what we have for translational motion, right? Which is that our net work equals our net force times the distance that we move, right, during that period of time. In this case, rather than using delta x, we're going to use delta s because that is, since we're moving along the arc of a circle, that's what we call movement along the arc of a circle, right, delta s. And we can take and keep this value the same if we multiply by a fraction that has the same value in its numerator as its denominator. So if we multiply times r over r, then we haven't done anything to net force times delta S, right? We've just multiplied by an r on top and an r on the bottom. But if we take r times net force, we know that that is our net torque, and our delta S over our radius is our angular displacement, right? So if we substitute those two things in here for those two terms, for our F net and for delta S over R, then we end up with this small equation right here. Our net torque times our rotation angle or our angular displacement gets us our net work. All right. So then we can apply that to get our work energy theorem in rotation. So our work energy theorem for rotational motion, again, derives from this net work equation, right? And we know that our torque equals our moment of inertia times our angular displacement. That's Newton's second law in its rotational form. And so we can plug that in for torque, and we end up with our net work equals our moment of inertia times our angular displacement times our angular acceleration, right? And if we take a look at one of our rotational kinematics, right, we know that our final angular velocity squared equals our initial angular velocity squared plus twice our angular acceleration times our angular displacement. And if we solve that for our angular acceleration times our angular displacement, then we have this term over here that we can plug in for alpha theta. And when we plug that in for alpha theta, we get to look at something else like this, which is our moment of inertia times that term. And if we distribute that term out, we end up getting something that, again, should look pretty similar to our work energy theorem from translational energy. We've got our net work equals the difference between two terms, one final and one initial, right? And if we pull those out, that gives us our kinetic energy. Our net work really is our difference in kinetic energy over the period of time that work was done. And each of those terms is our kinetic energy in terms of rotation. So our rotational kinetic energy equals 1/2 times the moment of inertia times our angular velocity squared. So let's compare that to our linear or our translational kinetic energy. And if we compare those two formulas, we see they're very similar, right? And now, just like with all of our other rotational motion equations, we have equivalents, we have analogs between our linear or translational variables and our rotational variables, right? And the first one is that, as usual, our mass is now being replaced by our moment of inertia, right? That stands in for mass in rotational motion. And obviously, our velocity is now replaced by our angular velocity. Right. Other than that, this is the exact same equation, right? And if we went and we thought about our units, right here, we've got 1/2 times our moment of inertia, right? Which our moment of inertia is the sum of our masses times radius squareds for all the point mass in that object. So that's in kilogram meters squared, right? And our angular velocity is in 1/seconds, radians over seconds. But remember, radians are kind of unitless. So that's 1/second squared. And that gives us, that should be kilograms. That gives us kilograms meters squared over second squared, which, if you remember, that is what we collapsed into joules because that's what we got from our linear kinetic energy, right? Kilograms is our mass, and then velocity squared is meters squared over second squared, right? Which also gave us kilograms meters squared over second squared, which we collapsed into joules, right? So both our rotational kinetic energy and our linear or translational kinetic energy are expressed in joules, which means they're compatible, and means that when we take two different objects and roll them down a slope, the initial gravitational potential energy that they have is going to be converted into translational kinetic energy, but some of that is also going to go into the rotational kinetic energy of those balls or spheres or whatever those objects are as they rotate their moment of inertia at some angular velocity, some final angular velocity down at the bottom. All right, so this is what we're going to play with today is rotational kinetic energy, and we are going to explore this during today's lesson.